Well, we're going to continue with Chapter 7 on alkyl halides, nucleophilic substitution reactions, and elimination reactions. So once again, my suggestion is that you return to that very first video that I created for this chapter, and it's entitled something like Preview and Review of SN2, SN1, E2, and E1 reactions, because you're going to need to know those. And so we're going to continue to build on those reactions, and you'll need to have that information that's in that very first short little video completely known by heart. You'll have to just know it. So, so far we have discussed the SN2 reactions. We looked briefly at some of the other reactions, just for comparison, but mostly in the terms of SN2. Now we've looked at E2 reactions. So these are the second order reactions. Now we're going to go on to the first order reactions. So that's going to be SN1 and E1. And we're going to look at kinetic isotope effects. This will be very briefly. 7-9 is the largest section in the entire chapter, and we're going to spend a lot of time on that, and very little on 7-10. So let's get into it now. So, unimolecular reactions. Consider the following reaction. Here we have substitution and elimination of this T-butyl bromide in ethanol solvent. So what you have is ethanol is going to be the nucleophile in this substitution reaction, and ethanol is also going to serve as the base in the elimination reaction. But notice that what you have is a tertiary alkyl halide. And so the first step, this is going to be a two-step reaction. The first step is going to simply be loss of bromide to form the tertiary carbocation, because it's going to be stable. In this case, the carbocation can form as an intermediate because it's a stable carbocation. Now, when you have these reactions in which the solvent, ethanol, also serves as the nucleophile, it's called a solvolysis reaction. Solvolysis. And in the vast majority of solvolysis reactions, it is going to be an SN1 reaction. So if you're looking at an exam question and you see it described as a solvolysis reaction, that's just sort of testing your knowledge to see if you understand the code that the word solvolysis means SN1. And if you do know that, then it's a huge hint in solving the question, solving the problem. Okay, so you know this is a neutral nucleophile. It is not going to be a strong nucleophile or a strong base. So you're not going to get an E2 elimination because this is such a weak base, and this being a tertiary carbon, a tertiary alkyl halide, you're not going to have SN2 reactions here either. And so the rate is going to depend only on this one molecule as it falls apart. It's going to simply lose bromide and form the carbocation. So the rate is going to be proportional to the concentration of this substrate, that reactant. First order kinetics. First order in the alkyl halide. So here's the mechanism drawn out. So the first step is loss of bromide to form the carbocation intermediate. The carbocation intermediate can then go on to substitution if the ethanol attacks here, the oxygen at the ethanol, or it can go to elimination if the ethanol abstracts a proton. So you can see that the SN1 and the E1 reaction have the first step in common, just as you saw on that little review video that I made for you. So here are the steps again. So this is the first significant step, loss of the bromide. Notice that bromide can attack here and go back. So this is drawn as an equilibrium. So then you have nucleophilic attack, and here, once that oxygen-carbon bond is formed, you're not going to have this loss. It's going to go on to product. So this step is not reversible. The entire mechanism is actually 3 steps, but usually this second step is not considered when you're counting the number of steps, or even frequently when you draw the reaction coordinate diagram, the energy diagram, because this is just a deprotonation step, very low energy back and forth. It occurs very rapidly at room temperature, and it's called solvolysis because the nucleophile is the solvent. So here are the first 2 significant steps. So you have loss of bromide. Notice this is the rate determining step. It's going up in energy because you're losing bromide. And here you form the carbocation. You actually have plus Br minus here. This has been omitted for some reason. And then you have nucleophilic attack by the solvent, and that is a low energy of activation. This will be a higher energy of activation. This is a low energy of activation. This is the rate determining step. And then you have proton transfer, which again is a very low energy of activation, and then it goes down into this energy well, a very stable product. So you do go downhill in energy. The first step is the rate determining step. Here, once again, this is the way that you describe the rate. S is for substitution, N is for nucleophilic, and 1 means unimolecular. It means 1 molecule involved in the rate determining transition state. First order kinetics. Let's see what's important on this slide. So this is an SN1 substitution. So if you have a neutral nucleophile, you're going to wind up with a cation, so you're going to have to lose a proton. So you'll always have a third step if the nucleophile is a neutral nucleophile. Here this is an anionic nucleophile. So you can have either one. You'll just have to remember that if you have a neutral nucleophile, you have another step to remove the proton. So you can also have loss of your leaving group to form the carbocation, and then your alcohol, or solvent, instead of acting like a nucleophile, can come in and abstract a proton to form the alkene. So oxygen attacks the proton, lending a pair of electrons here to form the oxygen-hydrogen bond. The pair of electrons in the carbon-hydrogen bond move back in and form the pi bond. This is the same kinetics. The first step is the same. The first step is the rate determining step. So this will be first order kinetics. So E1 and SN1 share the same first step. You can see here, once again, you lose X minus. Now you have both of the ions shown here in your carbocation, your reactive intermediate, and here, this is an energy minimum, energy maximum, energy minimum. So you go uphill. This is your E sub A. your energy of activation. Then you go over this smaller energy hill and then down to the products, which are much lower in energy than the reactants. And that's the driving force. Notice once again that the higher energy transition state corresponds to the higher energy product. The lower energy transition state corresponds to the lower energy product, which is normal. Remember, you have seen that the carbocation can rearrange when it's formed. And whenever you see this skeleton rearrangement, that is a hint to you that you had a carbocation. And it is not a single-step reaction. You have a two-step reaction in which a carbocation is formed, and when the carbocation is formed, you can get a rearrangement. So here, what happens is you lose bromide, you form the carbocation where the positive charge is here at this secondary carbon atom. You have a CH bond over here. You can have a hydride shift to move the positive charge over here to the tertiary carbon atom, where it is then attacked by oxygen and forms the CO bond. So this is the product after the 1,2 hydride shift. You'll also get elimination products. It's very difficult in these situations to get just one product, one type of product or the other, like either substitution or elimination. Usually you'll get both, and very often you'll get products of SN2, SN1, E2, and E1 reactions all. You're very lucky if you can fix the reaction conditions so that you just get participation of two different mechanisms. And sometimes you can just get one mechanism operating, but even whenever you have one mechanism, just one mechanism operating, you may get two products from that one mechanism. So that's one of the problems here, and that's one of the reasons why this is studied so much, is so that synthetic chemists can try to control the products that they get to maximize the percent yield of the desired product. So now let's look at this. Here we had a CH bond. Now we no longer have a CH bond. When bromide is lost here, it's at the positive charge is at a secondary carbocation. You do not have a CH bond to migrate. Notice that the hydride migrated preferentially to a methyl. So, because it's smaller, so it's easier for it to migrate. Here you don't have hydride to migrate, so you get a 1,2 methyl shift. So here is the methyl that came from this carbon atom. And once again, this is the rearrangement product where oxygen attacked at that tertiary carbocation after it was formed by the rearrangement. You're also going to have some of the unrearranged product where the oxygen has come in and attacked at the secondary carbocation, of course. So, what we saw on the previous slide is a secondary alkyl halide. The secondary alkyl halide gives rise to the secondary carbocation, and the secondary carbocation is stable enough to form for, a good amount of time. But now, when we have a primary alkyl halide, the primary carbocation is really unstable. And so it's not going to even really exist long enough for water to bump into the carbocation that's at the primary position. So the primary carbocation doesn't exist long enough to bump into the water. So this product is not observed where you would have water attacking at that position. So all you see is just the rearrangement product. And so what happens is the carbocation is formed here initially, and then one of the methyl groups migrates and the carbocation position is switched to here, which is a tertiary carbocation, and then that exists long enough for so that it can bump into the oxygen of the solvent. So that gives you some indication about the relative lifetimes of those carbocations. So here is the mechanism that's drawn out. Bromide departs. The methyl group migrates, the 1,2 methyl shift, like you saw. The methyl migrates with the pair of electrons in the carbon-carbon bond. So the positive charge is shifted to this tertiary position. Now oxygen comes in and attacks there and forms the pair of electrons, non-bonding electrons on oxygen, is used to form the carbon-oxygen bond here. Now, oxygen has 3 bonds to it. It needs to have only 2, and so another oxygen molecule picks up the proton, and you have the alcohol form. You're not ever going to have a proton just departing and floating off in space. You're always going to have something picking up the proton. This gives you a list of different solvents. So you can see from the dielectric constant, the greater the polarization of the solvent, the higher the rate, and so the polarization of the solvent stabilizes both of these ions, and so it makes it easier for the ionization to occur, and that's the rate determining step, and so it increases the rate when you increase the stabilization of these ions because of the higher dielectric constant. And then as you go down, you have acetone, which remember this is polar protic. You can see the protons attached to the high electronegative atoms. Here, this is polar aprotic. No protons attached to highly electronegative atoms in acetone or in ether. This is polar. This one is not so polar. Remember, the carbonyl is very polar because the pi bond in the carbonyl, the pi electrons are very loosely held and they are easily attracted onto the oxygen. And so this carbonyl is really polarized. So this is a very polar but aprotic. And so this aprotic solvent, even though it is polar, doesn't have any hydrogen bonding to stabilize the chloride the way that these 3 have hydrogen bonding to stabilize the chloride. They may stabilize the carbocation a little bit, no hydrogen bonding up here. And so the rate really decreases. And now this molecule isn't really even considered polar, it's just aprotic. And so it really doesn't stabilize. It stabilizes this ion pair even less, and so the rate drops even more. So this is a good comparison of how these different types of solvent impact the rates. And you could be asked a question about what is it that makes the rate so low in a particular reaction, in a particular solvent. Why is that particularly low? That would be a very good test question. You need to learn these different types of solvents. Learn these different solvents as well as the types of solvents that they represent. So here, this is an energy diagram that describes what I just said. Remember when we were studying the SN2 reactions just a couple of videos ago, I described to you how in a protic solvent, the reactants are stabilized due to hydrogen bonding. Now, in a polar aprotic solvent, they're not stabilized, and so the energy of activation is much less. So it makes the reaction go faster in an SN2 reaction. And also the attacking nucleophile is not covered by a hydrogen bonding solvent. And so then they both follow the same pathway down to the products. But the reaction is faster. Now over here, when you have a polar aprotic solvent, it's not the reactants that are impacted, it's the intermediates. Remember, the intermediates will be a pair of ions, a carbocation and an anion. Here, a carbocation and an anion. If it's polar aprotic, you will not have any hydrogen bonding to stabilize the anion. If it is protic, you will have hydrogen bonding to stabilize the anion, and so that makes the intermediates drop in energy, and that will pull down this entire part of the energy diagram, because this transition state is going to have some similarities to that, to the intermediates, and this transition state will have some similarities to those intermediates. And so the whole thing will be pulled down because it's in that protic solvent which stabilize the ionic intermediates. The better the leaving group, the faster the reaction occurs. And so this only makes sense. The rate determining step is going to be the departure of the leaving group. And so if you have a great leaving group, that rate determining step is going to occur faster. It only makes sense. The more stable the halide, the faster the ionization and the faster the reaction, because that's the rate determining step. Whether you're talking about SN1 or E1, it's the same thing. The more stable the carbocation intermediate, of course, it's the same thing, the same analysis, because the more stable the carbocation intermediates, the easier they are to form, and the faster the reaction will take place. Solvolysis reactions of primary and secondary alkyl halides are often just too slow to observe SN1 or E1 products. So in those cases, it'll do something else, or it just won't occur. You'll have no reaction take place. But tertiary alkyl halides, as well as benzylic and allylic halides, will undergo these reactions because they yield a stable carbocation, tertiary, stable carbocation, benzylic carbocation. It's resonance stable carbocation. Allylic carbocation, resonance stabilized carbocation. Okay, so these are easily formed. That means that those rates, the rates of the E1 or SN1 reactions, which these are intermediates in, will go more rapidly because the intermediates formed are more stable. So, so this is an example of the benzylic carbocation being formed. Here you have loss of bromide. You're going to have a benzylic carbocation formed where the positive charge is here, the positive charge is here. It's going to be resonance stabilized. And then you have the solvent molecule come in and attack and form a CO bond, or the solvent molecule can come in and abstract a proton from this terminal methyl and give you the alkene, which again is going to be stabilized due to conjugation with the benzene ring. So it's possible for the E1 elimination to give you more than one regioisomer. Remember, regioisomer, that means which region of the molecule does the double bond form in. Here is an internal double bond. This is a terminal double bond. And this is going to be the major product of E1 elimination. You're going to have both of those. And so the more substituted double bond here, this is a tri-substituted double bond, this is the one that's going to predominate because it is more stable than a di-substituted double bond. And you're going to get some of the substitution product. You almost always are going to get some of the substitution product. It's very difficult or maybe impossible to get only the elimination products in these E1 reactions. Now you cannot select to get one or the other way that you can in the E2 reaction. So you can't sort of stack the deck, remember the way that we could control which elimination product we got by using a more sterically hindered base, and we were able to control the relative ratios of these. Here it's impossible. This is just going to be governed by the relative stabilities of those alkenes. And so you just, these reactions are regioselective, but it'll change a little bit depending on the solvent and the temperature, but you can't really control it the way you can the E2 reactions. So here you can see you get this internal alkene and this internal alkene. These are the Z and E alkenes, and then you get this sort of terminal alkene. So there's 1, 2, 3 different alkenes possible from this reactant, in addition to the substitution product. Now, let's look at the formation of the carbocation. When you lose bromide, bromide will depart with the pair of electrons, and carbon bears a positive charge. And remember, this now is going to be an empty p orbital residing on carbon. The propyl, methyl, and ethyl will all lie in the same plane, at least the carbons of those groups will. And so now this carbocation is planar in the immediate vicinity of the carbon bearing the positive charge. And this is typical of all carbocations. They are planar intermediates. That means that the nucleophile can come in from either side. And so you're going to get both types of products. You're going to get the two enantiomers in about equal proportions. So you're going to get a racemic mixture. Now the nucleophile comes in. This one, notice you start out with the bromide going over to the right. So you're going to get some retention of configuration, and you're going to get some where the nucleophile has come in from the back. You're going to get some inversion of configuration. And as the bromide departs, the bromide is going to be here in this vicinity of the molecule for, a second or two, for just a very brief time period. And so the nucleophile, this is negatively charged. The nucleophile is rich in electron density. The nucleophile is going to be a little bit repulsed from this side of the molecule because it's just sitting there waiting to react. And so the bromide will repel the nucleophile a little, and that will make this just a tiny bit more likely to react with a nucleophile coming in from the back side, because the bromide will block this side just a little. But it's not much. At the very most, 5%. It's going to be a very small difference, but it has been observed. And so here it's demonstrated as the bromide departs, the nucleophilic attack here is hindered, but here it's easy to come in from the other side. And so you'll see, a tiny change. Sometimes it's just, 1% difference. Sometimes it's, I think the largest I've ever seen is a 5% difference. It won't be huge. But this is the explanation that's given for that. Okay, kinetic isotope effects. You're going to learn all of these mechanisms, and you may start wondering, how do we know that these mechanisms are taking place? Well, we have invented, discovered, developed different ways of studying these, and one of these is kinetic isotope effects, in which we'll run the reaction without an isotope present in the molecule, and then we will replace one particular atom in the molecule. We will have the molecule synthesized with a different isotope of that atom in that place, and run the reaction again and see how the rate changes. So one of the most common ones is deuterium. You know, deuterium is an isomer of hydrogen. And so, so we run deuterium isotope effects. And so, so deuterium is, it's a different isotope from hydrogen. So, you know, hydrogen is just a proton. Well, deuterium is a proton with a neutron. Okay, so it's H2. So deuterium is heavier, and you might think of it as larger, but it's not. The neutron is very tiny, and it's in the nucleus of the atom. So here we have, for an isotope effect study, you can look at this. Here we have a base coming in. It will abstract a proton. We say that it abstracts a proton from the beta position and form an alkene. Okay? And so now to run an isotope effect reaction, an isotope effect study, where we would go in and we would synthesize this molecule and replace the two hydrogens here with deuterium. Now, the carbon-deuterium bond is stronger and harder to break. And so, whenever we run this reaction, this is going to be the product here, where the base comes in, and instead of abstracting a proton, it abstracts a deuteron. Okay? And so, remember, this CD bond is stronger than the CH bond, and so it's going to be more difficult to abstract that proton. And so, what happens is, if you see the rate diminish a little bit, so that means that you see an isotope effect. If you see the rate diminish a little bit with the deuterated reactant, so what happens is so this reaction is about 7 times slower with these deuteriums. And 7 times slower, that's a significant rate retardation. And so the reason is because of the CD bond that has been replaced. And since the rate is slower, that tells you that this carbon-deuterium bond is being broken in the rate determining step. If it were broken in a different step, say after that abstraction, then it would not impact the rate. Let's pretend that the base that bromide left and gave you a carbocation intermediate. Well, that would be the rate determining step, and the CD bond would not be broken in that step, and so you would see no impact on the rate of the reaction. But what you see is you see a 7 times slower rate, rate retardation of a factor of 7. So the base comes in, abstracts a deuteron, and that pair of electrons moves over, bromide departs. This is an E2 reaction. And so, since you see the rate retardation in this reaction, that tells you that the carbon-deuterium bond is indeed being broken in the rate determining step, and that tells you that this is an E2 reaction instead of an E1 reaction, because in an E1 reaction, you only have bromide leave in the rate determining step, and the carbon-deuterium bond would not be broken in the rate determining step. Okay, so I hope that explains, and So in the next finishing steps, we're going to look at some, in the final video, which I'm going to create for you, we're going to look at some synthetic strategies, because that's the reason for studying all this. This is to tell you how to understand these reactions, how to predict what they're going to do, and then all of that is going to be used to be able to synthesize important molecules like pharmaceuticals. And so that's what we'll look at in the next and final video for this chapter.